All right, so last Friday we went over the idea of the atomic structure, and we went over the experiments first that were used to elucidate the atomic structure. And those experiments showed us that we've got this center part of the atom called what again? The nucleus, right? And the nucleus consists of both protons and neutrons. We know the proton has a charge of +1, a neutron's neutral. And then the electrons are kind of floating around the nucleus, and they have a negative charge. And we know electrons are tiny, itty-bitty. So the mass of a proton and neutron is about 1 AMU each, and then an electron's very, very small. So if you look at the periodic table, you can see the atomic masses listed in AMU. They're typically at the bottom corner. And then we said isotopes are defined as atoms or elements that differ in their number of neutrons. So hydrogen, in this case, can exist as 3 possible isotopes. Hydrogen 1 is the most abundant one, and then we've got hydrogen 2 and hydrogen 3. And then we wanted to go through and do some practice. So we said oftentimes you see these symbols that define an element with its mass number. And the mass number is in that top left-hand corner. That tells you the number of protons and neutrons. And then if you have a charge too, the charge will show up to the top right of your element. So if you've got extra electrons, your molecule or your atom will be negative. If you don't have enough, it'll be positive. And we'll go through and do more practice today. So let's go ahead and switch to the symbolic representation of atoms. And in order to do this, I really like drawing, so if you guys have colored pens and things like that, you're more than welcome to bring them out. But the first thing we're going to do is we're going to try to represent some atoms, and I'm going to color code my neutrons, protons, and electrons. So the first one we're going to do is we're going to draw lithium-6. Let me clean up this 6. And I'm going to do black for neutrons. I'm going to do red for protons. And I'm going to do blue for electrons. Now let's imagine we've got this atom. It's just a sphere of space right here. Let's try to fill up this atom with all of our subatomic particles, including electrons in here. So if we look at lithium, how many neutrons should it have? Lithium-6. So I have 6 neutrons? Yeah, it can be confusing, right? So 6 is the mass number. That's the number of protons plus neutrons. If we look at the periodic table, what's the atomic number for lithium? 3. So that means it should have 3 protons and 3 neutrons. So I'll go ahead and I'll do these kind of clustered in the center here. Okay, so this area right here we know is our nucleus. The vast majority of the space in an atom is not in the nucleus, it's just empty space. All right, and then how many electrons do we have if this molecule, or if this atom is neutral?
6.
Well, let's consider bouncing charges, right? So protons have a positive charge, electrons have negative. So we want to balance out the protons with electrons, right? So if we have 3 protons, we probably need to have 3 electrons in order for this to be neutral. Does that make sense? So the mass number is both protons and neutrons, but when we're balancing it, we only consider the protons. Okay, so we've got 3 electrons kind of floating around here, and they're in this kind of probability cloud of space. So I'll just put those electrons out there. All right, let's do another one in practice. This one's going to be tough. We're going to have a lot here. So how many protons and neutrons will we have? That's the first thing I would do. So let's start with protons. I think protons is easy. So if we look at chlorine, how many will we have? 17. That's an atomic number. How many neutrons will we have? 18. We need to add these two numbers up to equal 35. All right, how many electrons will we have then? 18, right? In this case, we've got one more electron than protons, which is why we have an overall -1 charge. So we'll do 18. Okay, so just really quick, we know this atom's going to be big. I'm going to go through and do my red protons. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Our neutrons are black, so I'll do 18 of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. They're all in that center clustered nucleus area. And then with our electrons, we've got 18 of them. They're kind of floating around in space. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you guys can practice with this. And a cool thing that's available online is this website called PhET. Has anybody heard of that? And I'll show you. It's a link on the notebook. But for example, you can go into the section called Building an Atom. And you can go over here, and it will give you protons, neutrons, and electrons, and you can actually build your own atoms and check to make sure that you're building the correct atom. So this is a really useful online tool. At the end of lecture or tomorrow, we'll go through and practice some of these. All right, let's do one more. Let's do an easier one. Doesn't take as much space. Let's do helium with a negative charge, specifically helium-5. So how many protons should we have for helium? 2, right? Atomic number 2, so 2 red dots in the center, those are our protons. All right, how many neutrons for helium? 3? Yeah, we have to have a mass number of 5, which means our nucleus should have 3 neutrons. And then how many electrons? 3, right? We've got to have one more electron than proton in order to account for that negative charge. So I'll just do 1, 2, 3. Does that make sense? Yep.
So is it always just one more unless it's like -2?
Yeah, so what happens, let's do another one, just really quickly next to it. I'm going to zoom out a little. So this one's helium with a positive charge. You can show it just with the plus or +1. It's fine either way. So we still have 2 protons, right? The protons define it as being a helium atom. We still have 3 neutrons because the mass number is 5. But now how many electrons do we have? 1, right? So normally, helium as a neutral atom has 2 protons and 2 electrons, but if it has a positive charge, that means it's missing 1 electron. So we would only show this with 1 electron out here. Does that make sense?
Yeah.
Okay. All right. I've got a short little video. I think it's kind of cheesy, but I like showing videos for this stuff. Let's see if the sound works here.
Welcome to Doc's Teaching Chemistry. Our second lesson is on the atom. All substances are made up of matter, and the fundamental unit of matter is the atom. Atoms are made of 3 smaller things: protons, neutrons, and electrons. Paige and Dexter are going to help build an atom. Protons are positively charged particles. Neutrons have no charge and are neutral. Protons and neutrons are located in the center, or nucleus, of the atom. Electrons move around the outside of the nucleus and are negatively charged. Electrons move about so fast that they form clouds that surround the nucleus of the atom.
Yeah, you know who would not do that? My dog. She'd just go in there and rip all the balls out and chew them apart. So I appreciate you guys humoring me with my silly videos. So there may be a problem on the exam where I ask you, all right, here's a symbolic representation of an atom. What atom is it? And then what's the mass number for it too? So be prepared to go either way, from the symbol to drawing it or from the drawn version to the symbol. All right, the story does get a little bit more complicated though. So right now we've shown these electrons in the dog video, they showed them running around. The reality is not all electrons are in the same type of area. In fact, we've got different levels that electrons reside in, right? So some of you may have heard this term before, but the term is valence electrons. Does anybody know what that means? What do you think? Yeah, exactly. So valence electrons are kind of defined as the electrons on the outermost of an atom. You've got electrons that are closer to the nucleus. Those tend to be a little bit more stable, less reactive, where the ones on the outside tend to react with other atoms. So let's take a look at a symbolic representation again. We'll do lithium-6. And we know we've got 3 neutrons, and we've got those 3 protons in our nucleus. And then in this case, we've got electrons, we've got 2 of them out here that are kind of in this inner shell. And then we've got 1 electron out here, so I'll just write it as E minus, in this outer shell. So some electrons are in inner shells. There can even be more than 1 inner shell. And then these electrons are in the outer shell, and they are a lot more reactive. The reality is that these shells can vary in shape and size too. So let's talk about the shells that these electrons reside in. And this can be a little bit weird to think about, but these shells are called orbitals. All right. So the first orbital, the most simple one, is actually just a sphere. And this is called an s orbital. And if an electron's in this orbital, really what this is a probability cloud. So this electron has a probability of being in any part of this sphere-shaped area here. Electrons move around super duper quick. It's really, really hard to know their position and momentum. And if you go on further into chemistry, you'll talk about that. That's called the Heisenberg uncertainty principle. But this s orbital is a good statistical map of where you can find that electron. The chances of an electron being out here are super duper slim, so that's not included as part of the s orbital. There are some other orbitals too that look a little bit different. And in order to show these, I actually have to use coordinate maps. So I'm going to do our y-axis up and down. I'll do our x-axis here, and then our z-axis kind of going back this way. So y, z, and x. And this orbital kind of looks like a dumbbell. So if you've got an electron, it's got an equal probability of being in the top lobe or the bottom lobe of that dumbbell. It can be anywhere in that p-type shape. Does that make sense? So in these p orbitals, we've actually got 3 different orientations. We've got one where it's going along the y-axis. Then we've got one where it's going along the x-axis. So I'm going to draw that really quick. And then one where it goes along the z-axis. And this one's kind of going in and out of the page right there. So we've got all of these different p orbitals. And the important thing to remember with orbitals is anytime you have an orbital, it can only hold 2 electrons inside of it. Electrons are kind of odd that way. They really, really, really want to be paired with another electron. So, for example, in an s orbital, that can hold 2 electrons. In this p orbital, the one along the y-axis, that can hold 2 electrons. In the p orbital going along the x-axis, that can hold 2 electrons. In the p orbital going along the z-axis, that can hold 2 electrons. So how many electrons can be held in all the p orbitals? 6 total, right? Because we can hold 2 in each of those different orientations, where an s orbital can only hold 2 overall, because there's only one orientation for an s orbital. We're not going to get super far into it, but if you are curious, you can read through your textbook, and they talk about orbital filling. And there's a specific order in which we fill these orbitals, too. So we start out with something called the 1s orbital, and then we go to the 2s orbital, and then we start filling p orbitals, and so on. If you go on and take general chemistry, you'll talk about it a lot more. So each orbital can hold 2 electrons. That's the most important thing. And then once an orbital is filled, you have to fill the next highest energy orbital. Or I'll say orbital set in the case of the p orbital. Okay, so each orbital can hold 2 electrons. Once an orbital is filled or an orbital set, then the next electrons have to go into a higher energy orbital. They can't be squeezed into an existing orbital. So there are these s orbitals, there's the p orbitals. Does anybody know of orbitals beyond that? There's actually an orbital set called d, so you may have heard that in high school. D orbitals kind of look like clovers, and you get into these weird shapes with rings around them. I'm not even going to attempt to draw them. You can see them in your book. And then even beyond that, there's these orbitals called f orbitals. If you look at the very, very bottom of the periodic table, those 2 rows, those rows contain f orbitals. Those are the only elements that have them. So we're not going to get into those too much. That's more for higher level chemistry. But this does get to an interesting point. And this is related to chemistry that was discovered in the early 1900s. And this is referred to as the quantum model. I know whenever people hear the word quantum, they think, oh my gosh, he's getting into really crazy chemistry. It's not entirely the case. Quantum model's very simple. And all it really means is that there are specific energy levels for orbitals. And then electrons must reside in an orbital. And the way I like explaining this is with the stair system. So let's imagine we've got a step of stairs like this. And let's say we have 3 electrons, right? Okay, 3 electrons. We can have 2 on the first step. We know electrons like to be paired with a buddy. But our third electron's got to go up to this next step. Really all the quantum model is saying is that it can't be halfway up a step. It's got to reside on a step itself. All right, and then if we look at these electrons, which electron or electrons are going to be the valence electrons? What do you guys think? I'll get back to you. Is it going to be the bottom two or the top one? Top one. Typically, the higher in energy you get, the more reactive they are. These are going to be considered your valence electrons. Yep.
Can electrons jump orbitals?
They can. So in order to get an electron to go up a step, what do you think you need to do? Yeah, you have to put some energy into the system, and then that electron can go up a step, but it still can't be halfway up a step. Typically, if you bump an electron up a step, the atom's not super duper happy. It wants to return that electron down to a lower energy level, and it can do that a variety of different ways. One is it can release heat. So basically, you put energy in, excite the electron up, and then it relaxes back down and emits heat. Another thing that's really cool is I'm sure some of you guys have seen like glow-in-the-dark stickers, or you've maybe even been to a place with a black light. Sometimes you can use light energy to emit or to push electrons up a step, and then when that electron falls back down to the lower step, it shoots a photon or beam of light back out at you, and you can see it glowing. So there's a bunch of different excitement and relaxation pathways.
And that's what the uncertainty principle. Like when you look at something that shoots light in it and push the electron into a higher orbit.
So your question was about the uncertainty principle?
Yeah.
The uncertainty principle is a little bit different. It's saying, essentially, if we've got an electron in something like an s orbital, we can't know where it's at and know its momentum. It's a weird thing, but electrons are very, very odd because they're super duper tiny. They don't behave like a particle. If you've ever studied Newtonian physics is awesome for large things or things that we can hold, so things in our day-to-day life. But once you get down to things that are super duper tiny, tiny particles don't behave well. They actually act more like a wave than a particle. So that's kind of why electrons are so weird. That's a good question, though. So let's make another note that valence electrons reside in the highest energy orbital. I'll put, the S in brackets here. So it can be one orbital or many orbitals. All right, so let me show you guys the easiest way to determine the number of valence electrons for a given element. So I'm an organic chemist. I don't really look at the middle part of the periodic table. I look at the ends. So this whole block here I just call transition metals. Can you guys see that block on the periodic table? It's kind of between 3 and 12 on there. Right now we're just going to block that off and just say, let's ignore those. And then what I want you guys to look at is the Roman numerals on the top. So we've got 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. All you need to do to determine valence electrons is to find that Roman numeral. So for example, group 1A, how many valence electrons do we have? 1. It's pretty easy. And this is assuming that the that the atom is neutral, right? So it doesn't have any extra or not enough electrons. It's assuming it's in its normal state. All right, what about nitrogen? How many nitrogen valence electrons do we normally have? 5. So you have to know your Roman numerals a little bit. Or you can just count over, right? So we could say, 1, 2, 3, 4, 5. So over here we know nitrogen and phosphorus have 5 valence electrons. One thing you may notice is as we go over, we get into 6, 7, and 8. Typically, atoms don't want more than 8 valence electrons. This is referred to as the octet rule. Atoms really like having an octet, but they don't typically want more than an octet of atoms of electrons. And we'll talk more about that when we get into bonding. So let's take a look at just some simple rules for valence electrons. And I'll make one for neutral atoms. For neutral atoms, like I said, it's this main group number. That's the thing in red, is equal to the number of valence electrons. That's pretty easy. It gets a little trickier, though, when we run into situations where we've got a charge on our atom. So what if your atom has a negative charge, or what if it has a positive charge? Then you have to add or subtract electrons from this number. And the easiest way, I think, is to make a little formula. Where all you do is you take the main group number and you subtract the charge. However, make sure that your charge has the appropriate sign. So if it's -1, this box should contain -1 in there, not +1. And then this will tell you your number of valence electrons. Okay, so let's take some examples. Let's take fluorine with a negative charge. How many valence electrons would that have? So let's go to the periodic table. Fluorine, its main group number is right here, right? It's 7. Okay, so we'll plug that in and we'll say, all right, that's 7. And then what's its charge? -1. We've got a negative and a negative, which turns into what? Positive. So 7 plus 1 means we've got 8 valence electrons. I see people make that mistake all the time where they forget to cancel out their negatives and turn it into a positive.
So what if that meant a -2 check? Would it be 1 valence electron?
Yeah, typically though you won't ever run into that situation. So the question was, what if we have fluorine with a -2? Essentially we would wrap around to the next row and it would have 1 valence electron. But we almost never run into that. That's a good question. Let's try another one. Let's try magnesium 2+. So what's the main group number for magnesium? 2. It's in group 2. All right. The charge is +2, so I put +2 in here. All right, so how many valence electrons do we have? 0. Or, another way of thinking about this is it also has 8 valence electrons too. So it can be 0 or 8. I'm fine with you drawing it either way. So basically what it means is that its inner shell is completely full and happy. So you will run into those situations where you've got 0 valence electrons or 8. Does that make sense? What's that? So if we look at magnesium, let me actually go over to the periodic table. And let's take away 2 electrons. So we go -1, and then if we go -2, we would hop over to neon over there. Can you see that? So if we take magnesium and we take away 2 of its electrons, it's behaving a lot like neon at that point. Neon, we could say, has 8 valence electrons. So 0 or 8, you can use either way. Really, atoms really want to have that happiness of full shells, and so they'll try to gain or lose electrons to accommodate that. It's very common. Yep?
I think I missed where you get the charge from.
So, for example, this +2 gets plugged in here. So main group number minus the charge, and the charge is always in the top right-hand corner. I have to tell you the charge. The periodic table is only for neutral atoms, but you may run into situations where a chemist says, oh, I'm dealing with magnesium 2+, and then you need to subtract or add electrons to account for that charge. Yeah, that's one kind of confusing thing with the periodic table is it's only for neutral elements. Okay, so let's take a look back at the periodic table too. We've kind of been digging into it a bit more, but we do want to talk about it in a bit more detail. So here's a periodic table I pulled from online. There are different ways of writing group numbers. You'll see the way with Roman numerals and then the way with just regular numbers. The Roman numerals, like I said, are really good for determining valence number, but group number can be represented either way. It depends on what periodic table. Some have one, some have the other, some have both. And then the other thing you may notice is this color coding scheme on periodic tables. We don't have them in our room, at least not to this extent. But what this represents is the different reactivity or classes of atoms in the periodic table. The first one on the far left, we'll box it. We saw the Brainiacs video where they put these in water and they all exploded. These are called the alkali metals. And obviously by their name, they're metallic, right? They're kind of a weird metal because they're very reactive. In order to move them around, you actually have to store them in oil so they don't catch fire. The next one over, this column is also very reactive, but a little bit less so. These are called the alkaline earth metals. Pretty easy. These ones, which you guys saw in my previous condensed periodic table, these are called transition metals. They're always in the middle. And then over here, we've got kind of the stair-step region. These are called post-transition metals. You guys are familiar with a lot of these. You've got aluminum and lead and things like that in there. And then in this other stair-step region, you're running into really weird compounds. These are called, atoms. These are called metalloids. What do you think a metalloid is? Is it a true metal? It's metal-like, but it's kind of hard to classify. It has some metal-like properties, some non-metal-like properties. So really kind of say we don't quite know a good way of classifying them, so we're just putting them in their own group. And they're always in the stair-step region of the periodic table. And then when we go over here, we hit the best part of the periodic table. I'm obviously not biased. These are our non-metals. And these are the essential elements found in biology, right? So carbon, nitrogen, oxygen, phosphorus, and sulfur. Those are the key ones. If you go into a healthcare field, you're going to talk a lot about those elements in particular. You probably won't talk very much about transition metals, although on occasion you will. And then in this far column over here, we've got halogens. And then last but not least, we've got the noble gases. At the very bottom of the periodic table, you've got your lanthanide and actinide series. We're not really going to get into those. Those are really, really heavy elements, and they're somewhat complicated because they've got f orbitals in them. They tend to be radioactive and aren't commonly used. So let's define some other things in the periodic table beyond just the groups. And I'll show you guys this other periodic table too. First one we already mentioned is a group. It's a vertical column. Let me change this. So the Roman numerals and the number. And they have similar reactivities. Just like we saw in the Brainiacs video, all of those metals exploded in water. The other thing that we just mentioned is that they all have the same number of valence electrons. Which is why we can use the group number to determine the valence number. This is very, very different than something called a period. Periods aren't vertical, they're not up and down, they're horizontal. And really they have different reactivities. They're very, very different from one another. And they have increasing number of protons left to right. All right, so let's go back and look at the periodic table that looked a little bit different up above. But before I do that, are there any questions on groups versus periods? I know it's nitpicky terminology, but it's important to know in case there's a word problem. So the periodic table that we see is kind of half true. The reality is that that F block down at the very, very bottom is actually squeezed in between the transition metals and the alkaline earth metals. So for example, this F block should be squeezed in right here, but unfortunately that would make our periodic table super duper long. So they just said, let's cut that section out and put them on the bottom because those are relatively uncommon elements anyways. But it's important to know that, right? So it should go cesium, barium, lanthanum, cerium, and then so on. It shouldn't go cesium, barium, and then to hafnium. A lot of students get confused with that. So really the periodic table should be a lot longer horizontally. The other thing to remember is that the periodic table is also a wraparound system. So if you look at hydrogen, helium, and then you wrap around to lithium, beryllium, boron, carbon, and then wrap around after neon to sodium. So it's a true wraparound system, which the 2D table doesn't always represent very well. Yep?
Where's that N that's above helium?
Oh, that's a neutron. Sorry, it's hard to see there. But they just show a neutron as being that subatomic particle that's smaller than helium. Yeah, that's a good question. But I like seeing it in this wraparound form. It kind of reinforces the idea that it's not a static 2D table. So let's define some of the physical properties for periodic groups. And some of these are super intuitive, so bear with me. First one, we'll do metals. Then we'll do nonmetals. And then metalloids. All right, what's a property of a metal? How can you determine that something's a metal versus a non-metal? Anybody want to help me? So it could be magnetic. Some metals aren't, though. If you've ever put a magnet up to an aluminum can, aluminum's still a metal, but it's not attracted to the magnet. So that can be used for some metals, but not all metals. Yep?
Typically solids.
Yeah, typically solids. With what weird exception? Does anybody know the liquid metal? Mercury. So mercury is that liquid metal. It's a little bit weird. That's kind of the exception to the rule. Almost all metals are solid except for mercury. And they're usually solid at room temperature, right? If you heat up iron, you can melt it, but that's under really extreme temperatures. All right. What about their density? Do they have large densities or low densities? Large, right? So they take up very, very little volume, but they have a large mass for that small volume. Okay, so large density. What about conducting heat? What's better at conducting heat, a metal or a non-metal? A metal. So if you touch a hot pan, that conducts heat really, really well. And oftentimes it's used for conducting electricity. We obviously don't have wires full of gases. The wires we use in our house and in our computer are metals, right? Usually copper wires are used for conducting electricity. The other thing is if you look at metals, they're usually shiny. Some of them are kind of dull, but for the most part they're shiny. And then the last term we're going to use is malleable. What does malleable mean? Yeah, you can manipulate it, right? You can pound it out, you can stretch it into a wire, you can bend it, you can twist it, and so on, right? If we take a non-metal, like carbon, if you look at the inside of your pencil, that's graphite, that's carbon, right? If you try to bend that, it just snaps, right? Those are non-malleable items. So let's go through and make a list for non-metals. We said that non-metals are not always solid. Sometimes they're gases, sometimes they're liquids, sometimes they're like carbon, like graphite pencils. So that's an easy way. They're not always dense. They're usually poor conductors with a handful of exceptions, and they're not usually malleable. So not always solid. Not always dense. They're usually poor conductors. And they're not usually malleable. You may be noticing that I'm using the word usually a lot. There are always exceptions, right? So if you think about a computer has a lot of silicon in it. So silicon-based chips are very common in electronics. You can make these conductors out of non-metals as well. Metalloids are obviously this in-between group. They really don't fall into any group particularly well, so we put them in that stair-step region, and they have both metal and non-metal-like behaviors. Does that make sense? I know it's fairly intuitive. All right, we have a couple more minutes, so I'll show you guys this game. I would recommend pulling this up on OneNote if you can. And then if you go through it a few times, chances are you'll be in good shape. So let's build an atom. So let's just pick one. Let's pick nitrogen, and let's pick neutral nitrogen. So how many protons should neutral nitrogen have? 7. So we'll go 1, 2, 3, 4, 5, 6, 7. So we got nitrogen. How many neutrons will nitrogen 14 have? 7. So 1, 2, 3, 4, 5, 6, 7. And then how many electrons? Did I put 6? Oh yeah, I did. Thank you. So now we're at a mass number of 14. And then electrons? 3, 4, 5, 6. Oh. And you can have this charge thing and mass number up. The fun thing with this is you can actually turn this into a game too. And I really like doing the question mark one. So what element has 10 protons, 11 neutrons, and 10 electrons? And then we'll make the symbol. Yeah, so Ne, what is Ne? Neon. So what's the mass number in the top left-hand corner? So up here in the top left-hand corner, would it be 10? Be 21, right? The mass number is number of protons plus neutrons. So we'll go up to 21. And then what about the bottom left-hand corner? 10, right? The bottom left-hand corner is the atomic number. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? And then for the charge in the top right-hand corner, will it be charged? No, we've got the same number of protons plus electrons. We can go check, and it gives us this smiley face. So you're more than welcome to use this depending on your comfort level. All right, I'll see you guys tomorrow.
Tom, do you